about Monday's lecture before I move into kinetics. We talked about enzyme mechanisms and the idea of the free energy of the transition state. Okay. We're going to start talking today about a topic that sometimes sends terror into the hearts of students, which is enzyme kinetics. And I hope I will be able to share this with you in a way that instead of casting terror, in fact, generates curiosity and even appreciation, because it's actually a very elegant and powerful approach to things, provided you don't let the math get you too worried. And I will try to hold your hand through the math and point out the most important parts of the math as we go along so that you can see the interesting parts and not get worried by the equations. It's not enough just that an enzyme can do something. That's what enzyme mechanisms looks at. It's also important how fast it does things. We're going to see later on that the control of metabolism depends quite a lot on being able to control how quickly or slowly a particular reaction goes. So it can be very important. The numbers that we can generate through enzyme kinetics can tell us two different kinds of things about an enzyme. They can tell us how quickly the reaction is going, and they can tell us about the affinity of the enzyme for its substrate. All of those properties end up affecting their function. An enzyme that's extremely specific but extremely slow would be a choke point or a narrowing gap to get down through a metabolic pathway. Sometimes that's what you want, sometimes it's not. We're also going to talk a little bit about inhibitors. These come in a variety of flavors, and I'll try to point you towards the most relevant numbers, but also to give you a feeling for why the different kinds of inhibitors matter and what they're telling us along the way. They're also kind of a laboratory mimic for a real-life phenomenon, which is allosteric regulation. We've already seen allosteric behavior in hemoglobin. It's going to turn out to be very important for the regulation of enzymes. Yeah. Oh, thank you for telling me, yes. If I'm, don't catch that earlier. Make sure you flag me. Okay, is that a good light level? Okay. Mr. Hi, AV, can we turn off the spotlights? They are not good. They are, in fact, bad. Okay, is that, he's getting them. In the meantime, is that better? Somewhat better? Okay. And you do all have the handout, I take it, for the, is there anybody who needs the handout still for this lecture? Okay, great. I'd still like the spotlights down if we can. Can we kill the spots? All right. It's probably a good idea to start looking at reactions from a simple perspective. And so we're going to start by taking the simplest possible reaction we can imagine, which is where you have an enzyme that can take A and turn it into B. And that might not seem like a very interesting thing to do, so let me just give you an example of something that does that. We have a 3-carbon phosphorylated sugar called glyceraldehyde 3-phosphate, which we're going to get to know much better. It's in glycolysis. It's very important that some of that can be turned into dihydroxyacetone phosphate or back. And the enzyme that does that is called triose phosphate isomerase. So its sole reason for existing is to turn one of these into the other. And we're going to see which one does what when, but we'll just treat it as going in that direction for now. This is a graph showing you the progress of a reaction. That is, you set up a test tube and you're looking at how that reaction is going as a function of time. AV guy? You? Hi. Kill the spots, please. Thank you. They should never be on that screen, ever. So on the side axis, on the lower axis here, on the x-axis, we have time, change over time. On the vertical axis, we have concentration. So for a reaction like this, where we're having A go to B, A is going to disappear as a function of time, and B is going to appear as a function of time. And you can measure enzyme velocity, we say, as a function of either one. That is, appearance of the product or disappearance of the substrate. Either one is going to measure the velocity, the rate of that reaction. So now we're going to get into just a little bit of math. In a simple case where A goes to B, we can speak of the velocity of the reaction as the negative rate at which A is disappearing, or we can give it a constant times the concentration. That is, we can in general describe the velocity of the reaction as some constant times the concentration of the substrate. If we start getting into a situation where we have more than one thing on each side of that arrow, the kinetics start to get a little more complicated. So let's imagine a case that's not very much more complicated, where A plus B are combined to make C. And in this case, the velocity is going to depend both on the concentration of A and on the concentration of B. So your final simplified form of that would be a constant times the concentrations of each of them. So now the kinetics is going to be a bit more complicated. How does the enzyme concentration come into all of this? Well, if we imagine a circumstance where we have an excess of the substrate, S, sort of a generic substrate, S, that's in great excess, there's far more of the substrate than there is of the enzyme. Under those circumstances, when you raise the enzyme concentration, you'll increase the rate of the reaction, as long as there's a vast excess of the substrate. And so you can see a linear dependence in that range of things. If, on the other hand, you hold the enzyme concentration constant, we have a finite amount of enzyme, and we're going to start from low concentrations of substrate and increase them gradually, we see a slightly different kind of a graph. And in this case, we're going to have a constant amount of enzyme. We're starting from a small amount of substrate and increasing that amount of substrate. And what we see is the velocity of the reaction increases, but it doesn't just go up as a straight line forever. Nothing goes on forever in biology. And instead what we see is this line that starts off increasing and then tapers like that. And if it should look a little bit familiar, because a curve like this is rather like a myoglobin binding curve. It's called a hyperbolic binding. And what we're seeing as this curve tapers off is what's called saturation. That is, at some point, the enzyme that you have in there, the amount of enzyme you have in there right at that moment, is going as fast as it can. You can't get it to go any faster by adding more substrate. The enzyme is saturated. And one way of thinking about that is to think about the state in between, that you start off with enzyme and substrate. They form an enzyme-substrate complex. And then something has to happen, and you get enzyme and product released. And we're going to unpack that a little bit more in addition. But the saturation is showing that what you've gotten into is a situation where all the enzyme is occupied. Any questions so far? Okay. So if we look at this in just a little detail, we can imagine starting off with pure enzyme and pure substrate. So it's empty enzyme, it's pure substrate. And what happens with time as we mix these together. We're going to see some concentration of enzyme at the beginning, some concentration of substrate at the beginning. The free enzyme will decline as we form enzyme-substrate complex. And once we've started to make some of that enzyme-substrate complex, we can start making some product, right? And as we let this go on over time, there's this region here in the middle where things are kind of steady. That is, you have a constant amount of enzyme and substrate, a constant amount of free enzyme that didn't get occupied or has recently been released, hasn't yet been occupied again, whatever. at a constant rate of release of product, a constant consumption of substrate in this steady state situation in the middle. That's not an equilibrium in there. That's a steady state. Things are turning over at a constant rate. Now, the concentration of that enzyme substrate complex is going to be determined by three things. You make enzyme substrate complex out of enzyme and substrate. And you make it from those two at a rate called K1 for the forward reaction to make enzyme and substrate. Once you have the enzyme substrate complex, one of two things can happen at that point. It can fall apart again, back to enzyme and substrate. That's called K-1 for the backwards reaction. Or it can go forwards and release product, and that's called K2 for the forward direction. So the actual concentration of the enzyme substrate complex at any one moment is going to depend on those three variables. What happens to that existing, how quickly that enzyme substrate complex is made from the raw materials, and how quickly it falls apart from the other things. Any questions? And then to keep in mind that in this middle part of the time of the reaction, we can speak of essentially a constant concentration of enzyme substrate complex. I want to show you this so you can see where it comes from. I am not going to expect you to reproduce the derivation. For some of you, this will make it all make more sense. If you are not one of those for whom it makes a lot more sense, be patient with me, and I'll try to show you the landmarks as we go along. So looking at the previous concentration, the velocity of the reaction when we're talking about the appearance of the product with time, the rate at which the product will appear at time will be that rate K2, the rate constant for producing the product, times the concentration of the ES complex. Now, at what rate does the ES complex change? Well, it's going to be a long term here. It's going to be the forward reaction of making it from enzyme and substrate and their concentrations. It's going to be the breakdown back into the enzyme and substrate with the backwards reaction. And it's going to be the production of product by K2. And that all is kind of a long term to work with on a regular basis. And so biochemists who spend a lot of time thinking about kinetics often choose to simplify this situation by simply setting it up so there is a concentration of substrate that is a great deal more than the concentration of enzyme, and then that allows us to look at a situation where the concentration of the enzyme substrate complex itself isn't changing over time. It's that intermediate segment in there that we are talking about. And then the rest of the derivation to get to the number I'm going to talk about is in the book for those of you who find that kind of development in mathematical terms more helpful if it's there. So when we use these three constants, the production of the enzyme substrate complex from enzyme and substrate, the breakdown back to enzyme and substrate, the forward reaction to product, we can combine those three constants into one constant. We call that one constant the Michaelis constant. We've got this little m down there for the Michaelis constant. And to make it look especially important, it's a capital K. That is defined then as two things, as the ratio of the things that break down the enzyme substrate complex. So K-1 and K2 are both things that will destroy the enzyme substrate complex, one way or the other. And K1, the thing that produces the enzyme substrate complex. So we can combine those three different constants into a single one called the Michaelis constant. And when we do that, we can then describe the velocity, the initial velocity of an enzyme reaction in surprisingly compact ways. We can look at the V0, the initial velocity of an enzyme reaction when you set it up, as really reflecting only the substrate concentration and two constants. One of those constants is the Michaelis constant, which is a reflection, as we're going to see in a sense, of affinity. And one is Vmax, the fastest the enzyme will go when it's completely saturated. So we've actually simplified that previous equation down to one that has a lot fewer variables and only a concentration of substrate itself. So let's take a little look at some more curves here. In this case, take a look at the graph. We're looking at substrate concentration down here. One of the things that makes kinetics a little bit, it takes attention, is you need to look at those graphs and see what they're labeled as. We've looked at graphs that are showing a number of different variables, and so you always want to look at what those axes are. In this case, we're relating substrate concentration to the initial velocity at a constant amount of enzyme, all right? And this is actually similar to what we were talking about in the previous one with substrate concentration, but we've got some more things labeled in it, or we've defined some new things. So again, as we start to raise the substrate concentration, we see an initial rise in the velocity. It starts to taper off with the substrate concentration approaching saturation. One of the points of realism in this textbook compared to some is that even at quite high concentrations of substrate out here, you haven't actually hit the Vmax, the conceptual Vmax for the enzyme. That makes it so one of the things that should strike us is that we can look at how much substrate it takes for a reaction to start going in a vigorous way. And just as we used the halfway point for P50, for the affinity for oxygen, just as we used a pKa for an affinity for protons, we're going to use the Km, which turns out to be at half the maximal velocity. So the Km for an enzyme is the concentration of substrate that will produce half maximal velocity. It's going to reflect both the efficiency at which it selects a substrate and in which it converts it into the product. And you can think of it as an affinity, a measure of affinity, especially when the rate at which product is made is a lot less than coming apart. So the Km turns out to be a way to think about affinities of enzymes. How much substrate does it take to half saturate it, or how tightly does it hold on to things? We can also look at another variable called the Kcat, which is the measure of how quickly the enzyme goes when it's fully saturated, and its units are per second, so it's so many reactions per second. And we combined Km, which is more or less a measure of affinity, with the Kcat, which is a measure of the actual efficiency of the reaction itself once the enzyme is occupied, into a number called catalytic efficiency. And that's the ratio of Kcat over Km. And that catalytic efficiency number allows us then to have a single number by which we can compare different enzymes to each other or different substrates for that given enzyme. One of the interesting things that comes out when we start to study enzymes this way is there are some enzymes that are only limited by the rate at which the substrate hits the enzyme. We call them diffusion limited. There's some that appear to be faster than diffusion. Superoxide dismutase is the enzyme that protects your body from superoxide, which is a really nasty form of oxygen. And the thought is there that the enzyme actually has an electrostatic surface that it uses like a tractor beam to pull in the superoxide. So, okay. So far we've looked at enzyme velocities in a graphical format that shows them in a direct representation of velocity over time or velocity over substrate or whatever. It's an intuitively accessible form because of the curvature sort of visually suggests saturation, but it can be difficult to work with to get exact numbers because it's hard to extract the exact values out of them. I'm going to introduce you to the Lineweaver-Burke equation, which is a way to transform a curved equation into a linear one. It is a useful way to think about things and compare them. If you want to get serious about enzyme kinetics, there are graphical interpolation programs that can take the actual raw data and, in fact, be better at treating those curved lines than we are. But the Lineweaver-Burke equations are still referred to frequently, and they are a useful way to compare certain aspects of enzyme kinetics. So if we start with the Michaelis-Menten equation here, in which the velocity of a particular reaction at that starting time is directly proportional to the Vmax, the overall catalytic rate when it's occupied, and the substrate, and inversely proportional to the Km, the tendency to hold on to its substrate, plus the substrate. What we can do is make this, represent this as inverses. So if we look at 1 over the velocity, so here is 1 over the velocity, we now can talk about an equation in this form where we can separate it out to this, which is a constant term, the ratio of the Km to the Vmax, times 1 over the substrate, times, and this is a constant again. 1 over Vmax is itself a constant. The overall form of this equation should sound a little bit familiar to you if you remember y equals mx plus b. This is the structure of an equation that will give you a straight line. Okay, and to show you that, let's graph it out here. This is what's called a double reciprocal plot. It's a reciprocal plot because we're looking at 1 over the substrate and 1 over V0. And it's a double reciprocal plot because both of those variables are being looked at as their reciprocals rather than directly. And what it's done is to turn that curved line into a straight one. And if you remember my talking about y equals mx plus b, we now can extract directly from the graph, with the precision that we have with the numbers and so on, ways to estimate Vmax and Km. So this is 1 over substrate. So this is low levels of substrate. This is high levels of substrate. Again, this is 1 over V0. So this is low velocities. This is high velocities. This place where it's intercepting that line is 1 over Vmax. You wouldn't be able to get there just by adding more and more substrate because it might precipitate first or whatever. But that will give it to you by a graphical interpolation. The horizontal axis is the reciprocal of substrate. Where it intersects is minus 1 over the Km. So we can read off the Km from this graph as well as the Vmax by using the reciprocals. And then the slope of this line is Km over Vmax. So the slope combines both of the variables at once. Any questions about this before we move on? Give you just a second to kind of absorb. Okay, let's go. So far, we've talked about a pretty simple reaction. We talked about one that A goes to B, pretty much. Many reactions involve a lot more parts and pieces. And so you need to bear in mind that whenever you, as the number of things involved gets larger, the mathematics is going to get more complicated. This is for one example of a very common kind of reaction. Some oxidized compound and some reduced compound are involved, and they come out where the X is now the reduced one and Y is the oxidized one. So altogether, you've got 2 substrates and 2 products. Or, for example, this is another enzyme called transketolase. These are its two substrates. These are its two products. And what transketolase is going to do is to move that 2-carbon fragment on top of that. You're going to end up with a 4-carbon and a 5-carbon fragment overall. But again, two substrates, two products. You can imagine the math starts to get a little bit more tricky. You're going to be able to speak about the Km for each of those substrates. The Km for this one might be quite different than the Km for that one, for example. If we were trying to draw out in sort of a schematic form how many different steps are involved in something like this, here we start off with a fructose 6-phosphate in the enzyme. You have a rate constant to form it, a rate constant for it to fall apart. You have a rate constant for it to go forward into the 2 and the 4-carbon piece, a rate constant for it to go back. You have rate constants for its releasing erythrose and having a 2-carbon piece here. You have a rate constant back for the recombination to this, and so on. So you have separate rate constants for every one of these different states of the enzyme. But you can still speak about an overall kcat from here to there in terms of the overall disappearance of this or the overall appearance of that. And just to make life yet a little more interesting, some enzymes don't obey Michaelis-Menten kinetics. And this is an example of one of them, or this is a generic example, rather. Here we again have substrate concentration on the bottom and a Vmax here at the top. And now, as we start to add substrate, there's a pickup in velocity, but not a lot. And then there's a greater and greater increase, and then it tapers off again. And we call this a sigmoid curve. It should look familiar from hemoglobin, which also had sigmoid binding. In this case, we're talking about sigmoid kinetics. And again, it often is going to be a sign that the enzyme involved has some kind of allosteric behavior. Somehow or other, there's a change in behavior with the binding of substrate. We can still think about the variables we were thinking about before. There's still a Km that will reflect what concentration of substrate does it take to get to half maximal velocity. We can still talk about Vmax. How fast does the enzyme go when it is saturated? So the concepts behind Vmax and Km are still applicable. We're going to measure them in different ways, but they're still applicable. That there's got to be some kind of an affinity for the substrate, some kind of rate at which the reaction goes when the enzyme is actually occupied. Okay. Any questions about that before we start getting into enzyme inhibition? So let's start thinking about enzyme inhibition. Enzyme inhibition can be something that's occurring naturally in the environment because there's a constant warfare among plants and animals, for example. Or it can be something that's happening in artificial reasons. We've decided we want to inhibit anything that isn't corn in the fields, for instance, or we want to inhibit an HIV virus. So enzyme inhibition is at least as important as kinetics by themselves, either because it's a natural break or because it's an artificial break that we put on things. I'd like to talk about several kinds of enzyme inhibition so you can get a feeling for both how flexible they are and what enzyme inhibition tells us about enzyme mechanisms as well as about how the enzymes are playing a role in metabolism. Now, there's one kind of enzyme inhibition that we call irreversible. And as you can guess, you can't reverse it. It's a one-way street. A typical way in which irreversible inhibition might happen is shown here. So here you have your chymotrypsin. We talked about that in enzyme mechanisms. It wants to cleave peptide substrates. DIPF, diisopropylfluoride, can fit into that active site, and the enzyme tries to make a reaction go. But when it does, it ends up with a permanently added on covalent molecule that's on there covalently permanently. One common way that that works is with a substrate analog. That is, DIPF kind of looks like a peptide. And in that case, you can understand why it would be binding at the active site. You can also get irreversible inhibition by things that react somewhere else on the molecule, somewhere on some other residue that's important for structure, that when it develops a ball in a chain, now the enzyme is dead. Enzymes like DIPF that bind at the active site and then become completely covalently attached are often called suicide substrates. That the enzyme commits suicide by trying to react with them. And they are permanent, or essentially permanent. Another important suicide substrate is an anti-cancer agent. Some of you may have encountered if you have friends or family who've had cancer. You may remember from our previous work that we need to have thymidine to make DNA, that it's uracil that's going to be in RNA, but thymidine that's going to be in DNA. And in order to make thymidine, we start from actually uracil. And this is deoxyribose 5-phosphate, or DUMP, for the uridine. And we need to change the structure of this pyrimidine ring. We need to add a methyl group to that ring. And if we can succeed in doing that, we now have deoxyribose 5-phosphate thymidine monophosphate. If you look at the structure of 5-fluorouracil and DTMP and thymidine, you can see that the structure of these rings is really rather similar, except here you see a fluorine. Fluorine is usually a hallmark of something that's about to kill something. And that's what can happen in this case, is that the 5-fluorouracil can kill that phenylate synthase, in which case, in that cell, that enzyme is dead until it gets degraded and resynthesized. Another kind of inhibition, and one that has maybe more metabolic significance, is competitive inhibition. And in its simplest form of thinking about this, it looks something like this. It is, one of its hallmarks is it is reversible. There are a lot of examples of competitive inhibitors, both in drugs and in herbicides and in the body. And in competitive inhibition, you have some enzyme and some substrate with some active site that fits that substrate nicely. And you have some inhibitor which can bind at the active site, but it doesn't react. So this enzyme can either be occupied by a substrate or it can be occupied by the competitive inhibitor, but it's only when it's occupied by the substrate that it'll make product or that it'll break down substrate. And so what does that look like kinetically? I apologize for the red and green. I tried to find this graph in some other color combination and couldn't, but at least it's labeled. We're going to assume for the moment that we're looking at a simple enzyme that has hyperbolic kinetics. Here's your uninhibited enzyme kinetics. You have substrate concentration here at the bottom. You have the V0 here. And in the absence of any kind of inhibitor, as we add more substrate, we start to get a higher velocity. It tapers off as it starts to approach the Vmax. And we can see that for the uninhibited enzyme, it has a Km right around here. That is, it only takes about that much substrate to half saturate the enzyme. If it is a true competitive inhibitor, if all it can do is bind to that empty active site, and that's the only thing it does, then some of the time you're going to pick substrate, and some of the time you're going to pick inhibitor. The more and more substrate that's around, the more likely you are to pick substrate instead of inhibitor. So for a constant concentration of inhibitor, this is what the enzyme will look like as you change substrate concentration. It will it will take more substrate to get the half maximal velocity, but the enzyme is still intact. And if you can get it saturated with the proper substrate, it will react with it. So the Vmax is unchanged. If the Vmax is unchanged, we know that the Kcat is unchanged, the catalytic constant. And so this is the hallmark of a pure competitive inhibitor. It can change the apparent affinity. That is, it takes more substrate to get to half maximal velocity, but it does not change how well it reacts once it's actually occupied by the substrate. Any questions? Okay. This might be actually a little easier to see on a Lineweaver-Burke plot, and this is also a chance for you to take another look at Lineweaver-Burke plots to get a feeling for them. Again, it's a double reciprocal plot. We have 1 over the substrate concentration on the bottom, and we have 1 over V0 on the vertical axis. And here we have the enzyme activity in the absence of inhibitor, and we can extrapolate it out to this point on the horizontal axis, which is minus 1 over the Km, a measure of its affinity. And it will intersect the axis at 1 over V0, which is 1 over the Vmax. So for something that's behaving as a pure competitive inhibitor, in the absence of the inhibitor, we have Km over Vmax. In the presence of the inhibitor, we have alpha Km over Vmax. That is, there's a constant alpha that represents or reflects the tendency for that inhibitor to bind at the active site. And what we can see from the change in that graph is that the Vmax has not changed. It still intersects at the same point on the y-axis, but we've moved the Km in. And remember that this is a reciprocal graph, so this is a larger number now because it's reciprocal, a larger number, a weaker affinity apparently, meaning it takes more substrate around to get to the Vmax, or halfway to the Vmax. Other questions? Okay. Now, one thing to keep in mind about enzymes is that, especially for ones that are somewhat reversible at physiological conditions, and a surprisingly large fraction of enzymes are reversible, is you can get product inhibition. That is, if A goes to B, when you start off with pure A, you're making some B, B will start to act as an inhibitor over time. And that's why we talk, all those graphs show V0, initial velocity. They're showing you the velocity of the reaction before you get significant amounts of the end product there. And so for this particular, we looked at the triose phosphate isomerase a little earlier in the hour. Here is glyceraldehyde 3-phosphate, the 3-carbon phosphorylated sugar. Here's the product, the dihydroxyacetone phosphate. This particular reaction goes through an ene diolate. So this is the ene, this is the diol intermediate. And here's an inhibitor for it, phosphoglycohydroxamate. And you can see that it looks a lot like the transition state. It doesn't look all that much like either the substrate or like the product. And that's going to be a common finding, that things that are analogs to the transition state are often very good inhibitors, good competitive inhibitors. How much better? Well, here's another reaction in which we're going from adenosine to inosine. Inosine can inhibit that reaction just by product inhibition, plain old product inhibition. Its Ki as a product inhibitor is 3 times 10 to the 4th. If you use instead this thing here, which looks like a transition state analog, you see here where you have that carbon with the 4 bonds, carbon with the 4 bonds. This looks a lot more like that transition state. Look at how much better. This is almost 1 billion times better as an inhibitor than the product of the reaction. So this clearly has a great deal of affinity for that enzyme. That's the simple one. Competitive inhibitors are fairly intuitive, I think, off the bat. You know, you've got someplace to do something, something else is taking up a fraction of the time, it won't happen as quickly or as often. But enzymes are complicated things, and they have more than one place on them for things to react. And so we're going to be looking at a couple of other possibilities and try to look at how those things fly. Let's say we start off again with an enzyme. So this is a free enzyme. And in the normal condition, we would bind a substrate and make an enzyme substrate complex like this. But this inhibitor is different from the ones we were just talking about. This is one that can bind at a different place on that enzyme. So here the inhibitor can bind to the free enzyme. It can also bind to the ES complex, to the enzyme substrate complex. And it's easy to imagine that if the inhibitor has bound to the free enzyme, that might affect its affinity for the substrate, or that if it binds to the enzyme substrate complex, it might affect how well that active site is going to produce the product than it would compared to the uninhibited form. That's kind of a complicated way of saying that some inhibitors can change both affinity and change the Vmax. Let's take a look at this graph then. Again, we're going to look at a simple hyperbolic curve again. So this has a particular Vmax in the absence of inhibitor. It has a particular Km in the absence of inhibitor. It doesn't take very much substrate to saturate it normally, and it chugs along at a nice brisk Vmax. In contrast to what we saw in the case of the pure competitive inhibitor, when we look at the enzyme activity now in the presence of the inhibitor, we find two things are now true. There's a different Vmax. You can see it sort of trailing off into the horizon there. But it's pretty clear it's never going to get up to the Vmax in the absence of the inhibitor. So you can believe that number is a believable number. But on top of that, it takes more substrate to even get to that lower velocity. And so we would say that in this case it has a lower affinity for the substrate, doesn't bind it as well, and it is less effective at turning substrate into product when it has bound it. Now, is this an unrealistic situation? Well, if you remember the fact that there are lots of enzymes that have more than one substrate, there are lots of enzymes where something could bind at somewhere else than the active site of the first thing you're thinking about. And so what might be a competitive inhibitor at this site might act as a mixed inhibitor for a different site. So if you remember that one enzyme can have several different binding sites on it, you can see that enzyme kinetics can start to get kind of complicated when you think about different things binding at different sites. People have any questions about this example before I move on? You could imagine a case in which the inhibitor only bound to the enzyme substrate complex. If the inhibitor only bound to the enzyme substrate complex, possibly its only effect was on whether the catalyzed reaction happened or not, on K2, the forward rate reaction, or how likely it is to fall apart. In that case, you can have inhibitors that only change the Vmax. The enzyme still has the same affinity for its proper substrate, but it's not as good at making product. Okay. I've added in some things. I don't think these, I can't remember if these are in your textbook, but I'm having them here in any case. This is a way of having a language to talk about these things with. You can imagine starting off with your free enzyme and free substrate, and if you add an inhibitor to the free enzyme and free substrate, one of the things that could happen is you make an enzyme inhibitor complex instead of an enzyme substrate complex, and the substrate is still out there free, floating in the breeze. And for that reaction, we have a Ki, an inhibitory constant, that's specific for the one between the free enzyme and the enzyme inhibitor complex. We can imagine that once you've made the enzyme substrate complex, an inhibitor can bind to the enzyme substrate complex, and now we have this complicated enzyme substrate inhibitor complex. And that will happen at some rate, which we're going to call K prime I. This is a separate inhibitory constant. For the moment, we're going to treat them as separate possibilities. And it's always going to be the case that it's only the ES complex that's going to give you the enzyme and product then. Or for the math here, we're going to treat it that way. So if we use that kind of terminology about it, I'm not going to ask you to memorize these definitions. This is here so you can see how you can speak about it explicitly if you want to talk about all the variables explicitly. Here we're looking at the first inhibitory constant, the one between the free enzyme and the enzyme inhibitor complex. Here's the second, the K prime I of the second one where you bind to the enzyme substrate complex. And all that the alphas are talking about is there's a factor of inhibition that's going to depend both on the tendency of it to do that and the concentration of the inhibitor. So the alpha puts into one number inhibitor concentration and how good an inhibitor it is. All right? In the case where there's only a Ki, where it only binds to the free enzyme and makes an enzyme inhibitor complex, we can talk about that as competitive inhibition. The Vmax is going to look the same, but there'll be some reduced or some altered Km. It will actually be a larger Km because it has a lower affinity. We mentioned briefly the non-competitive inhibitors where only the Vmax was altered. Here you can see there's an alteration in the Vmax, but the Km is unaltered. We talked about the mixed inhibition, and maybe one way to remember mixed is the fact that there's a change in both the Km and in the Vmax. I'm not going to discuss the uncompetitive as yet another flavor. It's one in which there's only binding to the enzyme substrate complex, but I'm not going to go into detail. It also would have alterations in the Km and the Vmax, but their exact description would be a little different. Probably the most important thing to take away from this table, apart from the differences between, competitive and mixed and non-competitive, is that the Km, the affinity, is a separate variable from the Vmax, how well the reaction goes when the enzyme is saturated. Those are separate variables. You can have an enzyme with a high affinity but a low Vmax, and an analogous one that has a high affinity and a high Vmax. You can have two enzymes with the same Vmax but different Kms. They are independent variables. I'll pick up there on Friday.